I started to use it.
All right, we're back. I hope. So I'm letting you know right now, midterm will not cover anything from this exact second on until the rest of the evening. Okay? So the first half is fair game. Just letting you know. Yeah. If we're converting it to an NFA, yes. Yeah. And if it was T goes to single terminal A, then it'll go on A to that final stage. No, with A. If it happens to be T goes to a single terminal A. Yeah. Yeah, it's whatever the single thing is, either epsilon or a single terminal. Other questions before we take the next chapter on? Yeah, that past second. Other questions? Cool. So how do we generalize regular grammars into something that we can guarantee recognizes more than the regular languages? Well, what I think was kind of annoying was the rule types. So what we said was we can only have a single terminal at most or a single variable at most. And they have to be terminal followed by variable if you have both. That seems kind of annoying. What may be a nice idea is let's put anything you want on the right-hand side. Have a variable with whatever mix of variables and terminals you want on the right-hand side. So I'm going to motivate this with a very small example. So the alphabet here is 0, 1, and of course the variable is the only variable s. What is the language of whatever grammar this is? Well, let's see. Let's see. It generates a 0, and it, at the exact same time generates a 1, then goes in. Then s can either go away or 0, 1, go in, 0, 1, go in. Oh, what language is this? 0 to the n, 1 to the n. Is this language regular? No. And we proved that last time. So by allowing a single character on the right-hand side after the variable, we get a non-regular language immediately. So that tells us that this generalization of putting whatever you want on the right-hand side, that's a good one to do. So these things are called context-free grammars. So exactly the same as regular grammars, except R has rules of the form, some variable produces something, x, and now we need to say it produces x, where x could be any mix of variables and terminals. So how could I say any mix of variables and terminals? Star. And as many as I want. Star. Oh, what set should I star over? Sigma and the variables. Because I want any mix of variables and terminals. Oh, so where A is a single variable and X is variables or terminals in any order. And as many as I want. So regular grammars are a very small subset of possibilities of what a context-free grammar could do. Oh, let's see. Let's define some more things about this. So, like as an example, we can have a rule that looks like we can produce some terminals for a while, then have some other variables, maybe multiple times, then some more mixes, and I can have the right-hand side be as long as I want. So, and the mechanics are exactly the same as regular grammars. See why it generalizes so nicely, where I replace that one variable with whatever on the right-hand side it corresponds to. So if I wanted to apply this rule, I would replace that occurrence of variable A with a whole bunch of other stuff, this right-hand side. So that kind of tells you something interesting. Could I have multiple variables in a given derivation so far? At any given point, the currently derived string, could it have more than one variable? Yes, because if I apply this one, then I'm going to remove one, then add 6 more. So I may have a lot of possibilities as to what variable I'm going to start working with. Whereas the grammar we talked about right here, this context-free grammar, there was still only one variable, but in general, I may have more variables to work with. Any question? Yeah.
Wouldn't that make your string infinite if every time you just kept putting in more?
Well, I may have other choices of rules. So I may have like a simple one like that. These are the rule types that are allowed. I can have anything I want on the right-hand side. Other questions? Okay. So we need, like we defined before, we defined derives a particular string of terminals. Let's do this same thing here. So we say that, well, I might not have a single variable at a current moment. So let's say I have a mix. So let's say W1. And we're going to say it derives in 0 or more steps, W2. If W1 equals W2, in the case of 0 steps, or there exists W3 such that W1 in one step makes W3 and in other steps produces W2. So this is just a similar idea as what we did for regular grammars, except now we may have more than one variable on the right-hand side and more than one terminal on the right-hand side. So we got to work with all those possibilities. So we say that a given string of variables or terminals produces another one if they're both the same, or you can work with one application of a rule, and then you can work with the rest. So it's a recursive definition, yeah. It just means you can derive it in 0 or more rule applications. Yeah, so it's defined exactly the same thing as for regular grammars, but we're applying it with anything on the right-hand side this time. Cool, other questions? So then the language of a context-free grammar, G, and we're going to call it Ella G, is the set of all strings in sigma star such that S in 0 or more steps can get W. So all the strings that are full of terminals, and S can make them. So exactly the same thing as for regular grammars, but we're going to define it formally for context-free grammars. Anyone have any idea why they're called context-free grammars?
Because they're kind of disassociated or distinct from, like, everything.
It's totally fine. What if I applied this rule, A goes to stuff, and then I tried to apply some rule where I replace D with other things? Does it matter what's on the left or right of where that D is? Like, does the ABC on the front matter? What rule I pick for D? No. So that's where the word context-free happens. There are grammars, which we may not get to, called context-sensitive grammars, where it is sensitive to context. but here we'll talk about context-free grammars. Okay, then a language is a context-free language, or a CFL, if it is the language, I use language 3 times in the same sentence, of some CFG. So if I have a context-free grammar, whatever language it is, by definition, it is a context-free language. Just like with DFAs, regular languages are the language of DFAs. Context-free languages are for context-free grammars. Same thing. Okay? Well, by our example above, 0 to the n, 1 to the n is a CFL. Why? Because we made a CFG for it. So this is a great exam question. It's not on the midterm. But how do I relate regular languages and context-free languages? Is there something we could say? Yeah. Exactly. So, claim every regular language is context-free. Why is that true? No, you're almost there. You're almost there. Right. So for regular languages, can I make a regular grammar for it? Yeah. If it has a regular language, there's a DFA for it, and we outlined a procedure on how to convert any DFA or AFA into a regular grammar. Is every regular grammar a context-free grammar? Yeah, by definition. It doesn't have to use complex rule types. Those are just the things that you could have. So the proof of this is just every regular grammar is a CFG. It's a quick proof. Is it a proper subset? I didn't define that. I'm informal here. Is there a context-free language that isn't regular? Yeah, an example, 0 to the n, 1 to the n. So, the set, so I'll define it formally here. Set of regular languages form a proper subset of the set of CFLs. Because we know every regular language is a context-free language, and we know of a context-free language that isn't regular. So we really do have a model that does exactly what we could do before, but can also do more, which is pretty exciting. I think it's exciting. Yeah.
Next to proof, what does the RG stand for?
Regular grammar. Yeah, so I should, that. Yeah, if my handwriting is atrocious, please tell me. Other questions? Okay, let's do some examples. So we did one for 0 to the n, 1 to the n. Let's do this one. So this one's pretty cool. So again, a single variable, but we have more rules this time. So our alphabet is A and B here. So the two rules, replace S with ASA or S replace with BSB, or make S go away. Okay? What is the language of this grammar? Well, let's think about it. Generate whatever character. Am I going to generate the exact same character on the other side? Move in. Is it the same character on both sides? Go in, go in, go in. Palindromes. So this is the language of palindromes. So informally, formally, so L of G here is W reversed, where W is in AB star. So the set of all strings, and I want the ones that are palindromes. They're equal to the reversal. Okay? So let's see. So let's try to derive, as an example, A, B, A, B, A, which is a palindrome, so we should be able to get it, yeah.
So single character, not a palindrome?
Great job. Thank you. So we need to add the rules A or B. Thanks. Actually, if I left it as is, what would it be here? Even length. What is this language right here? Is that the same language?
No.
You sure? Is it the same language? Yeah. W plus the same string reversed, is that always going to be even in length? Yes. So this is actually the correct language for the original grammar. But if we go to a different color and put A or B like this, then we would say that L of G equals, so we need to be more careful here. We need to say for all strings in A, B star, where W equals W reverse. Yeah, thank you for that. So there is a slight difference between these two. The first one is even length palindromes, and the second one is any length palindrome. Okay? Are these languages regular? And don't say, just because that grammar is not regular does not mean anything. Sorry, that grammar is not a regular grammar. That doesn't imply anything. There could be another regular grammar somewhere. So these languages are not regular, and I'll give you some help for that. So for this one, you choose the string. S is A to the P, B to the P, B to the P, A to the P, in both cases. And why would this let us pump out of the language? Or either language, really? Where can I pump only? The first set of A's. If I put more A's into there, will it still be a palindrome? No, and that's the proof. You have to be more formal than that, but that's the intuitive idea. So now we have quite a few, yeah, go ahead.
Why is the first A is the only place that you can pump?
Because remember that X and Y have length at most P, and it's a prefix of the string. Other questions? Cool, so we actually have quite a few examples now of languages that are not regular, but are context-free because we just made a CFG for them. Sweet. So let's talk about one more, which will get us into some other topics. So let's talk about this one. So it's a little hard to draw correctly, but let's try anyway. So this is the first example where we have the same variable twice on the other side, and our alphabet is parentheses. So The three rules are replace S with left parentheses, S, right parentheses, or replace S with 2 copies of S, or make S go away. Okay? Any guesses as to what language this guy is? Balanced parentheses. Well, let's see why. Is the empty string balanced parentheses? Yeah, trivially. If S inductively is a set of balanced parentheses, would putting an extra pair be still balanced? Yeah, certainly. If S is inductively balanced, concatenating them, is that still balanced? Yep. So this is the set of balanced parentheses. Okay, so let's actually do a derivation of a string, and then we'll start to see other things as we go along. So let's try to derive the string, oh, I don't know, left, left, right, right, left, right. So where do I have to start no matter what? S, that's the only variable anyway, so I only have one choice. Which one should I do? SS, because if I tried to do the first one, well, I'll get the first and left correctly, but this middle part will not match up because it's not a balanced parenthesis. So I better do SS. So what we're thinking of doing here is having the first S be this part and the second S be this part. How many variables can I replace at any given moment? One. Which one should I do? First one or the second one? Does it matter? No, that's a question. Does it matter? No. That'll actually be a problem, and we will explore that in a bit. But let's say that we apply the second S first. So we'll have S, left, S, right, and then now we still have 2 S's to work with. So maybe now I'll try to go against the system, I guess, and work with the first one. So I'll have left, S, right, and I'll still have left, S, right on the second part. Well, then now I still have 2 S's. Let's alternate. So let's do the second one. What should that be replaced with? Empty. So that's going to go away. Left, S, right, left, right. And then, now what? Left, S, right. Left, left, S, right, right. Left, right. And then now we can see we apply empty. How many of you have taken 340 or a similar class before? Oh, so most people. So these things, CFGs, are used everywhere. They're used in like every compiler, kinda, that you've ever seen, and they're used in many other systems. So if you want your compiler to check whether your program's syntax is correct, is it a problem that we have 2 choices potentially of, yeah, and balanced parentheses is pretty important because we deal with parentheses and curly brackets, and we better make sure that's balanced. So it better get balanced parentheses correct. Okay? So what we're going to call a leftmost derivation is we're going to apply the leftmost variable in the derivation every single time. So unlike before where we worked with the right variable, the second variable sometimes, we're going to work with the left one every single time. So a leftmost derivation is a derivation where the leftmost variable, am I repeating myself? Leftmost variable is applied with a rule. Okay. Could I have done a leftmost derivation here? Yeah. Could I do a leftmost derivation of any string in any CFG? Yeah. Why?
It's always the first one.
Well,
First one.
well, it's the leftmost variable. Could I get something different if I pick some other variable? No, because it's context-free. It doesn't matter which variable I replace. So if I do the leftmost one, that's certainly fine. So there's a leftmost derivation for every string that has any derivation. So that's good. Well, it seems also a little bit tedious to work with this derivation thing, and it's tedious to write out. Does anyone know another way we can represent a derivation of a string? A parse tree. Something that's actually used in a compiler anyway. So we're going to work with parse trees for a second. So let's try to work with the same string. So I'm going to make it a little smaller so I can see it. Actually, I'll just copy it down. So let's work with this. So at the root of any parse tree is the start variable. And what we're going to do is we're going to repeat the same derivation, but as leaves and sub-parse trees of this parse tree. So let's see, we applied S to SS first. So there are going to be two children of this root S called S. And then we saw that we applied left S right to the right S. So we're going to have left S right there. And then we applied it on the left S. So we have left S right. And then we replaced that second S with empty. And note that terminals in a parse tree are always going to be leaves in the tree because I can't apply a rule with them. So the empty string is not a terminal, but it'll be a leaf of the tree, as well as the left and right parentheses in this case. So and then we did one more, should be left on this side, S right here, and then empty here. So this thing is a parse tree. Okay? Let's see. If I have a parse tree like this, how do I find out what string was produced? Just read the leaves. But in what order? From left to right. So if I read the tree like this, then read left to right gives the derived string.
So pre-order or in order?
Yes, it's an in-order traversal. Mm-hmm. Yes.
Are we only going to be doing leftmost, or do you also want us to do rightmost?
We're only doing leftmost derivations.
Okay.
Because what is the relationship between leftmost derivations and parse trees? From a leftmost derivation, can I get a parse tree? Yeah, because I read left to right. What about the other way? If I have a parse tree, could I get a leftmost derivation? It's exactly the same thing. Read left to right. Oh, so therefore, leftmost derivations and parse trees are in one-to-one correspondence. So we can interchangeably talk about leftmost derivations and parse trees. What is not the same is any derivation. It's not necessarily equivalent to the number of parse trees for a given string. But leftmost derivations are. So we're going to be talking about leftmost derivations. And it doesn't change anything because any derivation has a leftmost one because of the context-free grammar. Questions so far? Sweet. Let's talk about something else. Well, kind of related. Well, like we talked about before, it's kind of strange how we could have two different possibilities of something that could be derived in terms of normal derivations, not necessarily leftmost derivations. But could I get two leftmost derivations? Because that corresponds to two different parse trees, and our compilers don't want that because they deal with parse trees. Well, consider the string, the empty string for this grammar. Could I have two leftmost derivations, different leftmost derivations for the empty string here? Well, let's see. I have s going to empty directly, but do I have another way? Yeah, what's the other way? S goes to SS? Well, I had better fix the left S first. So that's going to give me S, and then I can give the empty string after that. That's kind of annoying, especially for the empty string, but because I love the empty string. But for any string that we want to derive, if we have two leftmost derivations for it, then there are two parse trees for it, and that's kind of annoying. So we're going to call a grammar ambiguous if there is some string in its language having at least two different leftmost derivations or parse trees, because they're the same. So we would call that grammar ambiguous, the one for balanced parentheses, because we had the empty string, at least one string, having two different leftmost derivations and or parse trees. So that's kind of annoying. So something you should note. Do not call a language ambiguous, because for this language we can actually get a unambiguous grammar, and we'll see one in a second. So there are languages called inherently ambiguous languages for which every grammar for them is ambiguous. We're not going to talk about those because it's actually quite difficult to prove whether one is inherently ambiguous or not. But we call a grammar ambiguous, not in language. Okay? Cool. So I actually didn't write it down, but I remember it. So can we make a unambiguous grammar for balanced parentheses? So let's try. Well, what string better I have in this language? The empty string. And there better be exactly one way to generate that thing. So let's generate it outright. Well, let's see. I gotta generate some balanced parentheses here. Well, if I produce a left parenthesis, there better be some right parenthesis to match it, right? There better be some right parenthesis to match it. But what better go in the middle of those two parentheses? a balanced set of parentheses, or S here. So S better go there. But now we're back to where we started, but now let's try to fix this. So the problem we had before was where we had this other S on the right-hand side. So what can I do to fix this rule to allow that to happen?
You only duplicate if you had.
Well, what if I put an S right there? Because, well, here, this is pretty obvious why we should make an S there. But if we put another S on the right-hand side, then what happens after that left and right parenthesis better be a balanced set of parentheses as well, because of the SS rule that we had before. So, is this grammar unambiguous or not? Well, let's check. Does it unambiguously generate the empty string? Yeah. I couldn't use the second rule because it generates 2 characters, so that doesn't work. So the empty string is good. But what about any set of balanced parentheses? Are they unambiguously generated? Well, let's assume that S is unambiguously generated in both cases. Do I have 2 different leftmost derivations? Well, if I have a leftmost derivation for S in both cases, I have a leftmost derivation here because I have a unique S to pick here. So therefore, this grammar is unambiguous because I have a unique leftmost variable to pick. And once I pick that, then I can go all the way down to where I have the empty string, which is unambiguously generated. So the only problem we had before was that the empty string was the only string I claim that is unambiguously generated. But, and the problem was that we can apply this SS rule up here. But in order to get rid of that, we needed to have something after when we generate a balanced set of parentheses, something that also is also balanced. So by putting an S after, now we guarantee that anything longer than the empty string is unambiguously generated, and the empty string is unambiguously generated. So this grammar is unambiguous. Questions about this? Yeah.
So it's unique because it's not just 2 S's together. Either one can go to epsilon. This one's got parentheses.
Yeah. Well, it's not that anything longer than the empty string has 2 different leftmost derivations. It's that when we get down to the empty string level, then we can make 2 different leftmost derivations. It's not the only string that had a problem was the empty string before, and that was because of the SS rule. But by putting this S here, we fixed that problem. Okay? Yeah.
So which one is contained in which? The ambiguous and unambiguous grammars? Are they equivalent or?
No, they're actually not equivalent because there are languages called inherently ambiguous, which say that every single grammar for them is ambiguous. There are no unambiguous grammars for them, unfortunately. So, and something that we'll actually see in a few weeks, suppose I was asked, so we have grammars that are unambiguous or ambiguous, or languages that don't have any unambiguous grammars. Suppose I tasked you, if I was really mean, to take a grammar as input and tell me in a finite amount of time whether it is ambiguous or not. That problem we'll see is undecidable in general. So compiler writers have a really hard time because they got to make an unambiguous grammar for whatever language they're working with. So this problem in general is undecidable, making this a really tough thing to work with. But any questions about ambiguity? Yeah.
That's kind of like a general question. If you have a grammar with like the minimum number of rules for a language, is that going to be unambiguous?
Not necessarily. And another problem, suppose I tasked you with saying, if I give you a grammar and I ask you, does this grammar have the minimum number of variables or the minimum number of rules? That's also undecidable. So we're starting to hit the undecidable problems here, but we'll get there eventually. But any questions about this example?
So, real quick, the explanation for why it's unambiguous is because there's a unique leftmost variable.
Well, there's always a unique leftmost variable. The problem before was that when we got all the way down to the empty string, we had multiple ways of getting the empty string.
Okay.
But here we don't. So since there's always a unique leftmost variable and a unique thing to do with it, then therefore this grammar is unambiguous.
Okay.
Yeah.
So could you pick anything other than the empty string and have it be unambiguous?
It generated it unambiguously, yeah. The original grammar for anything other than the empty string did it unambiguously. Because for anything that was concatenated, you had to do the SS rule. And for anything that was just within two parentheses, you had to do the first one. It's just when we got down to the empty string where problems start to happen.
So if anything in the set of languages is, it has two derivations or whatever, it's all by all ambiguous. So
I'm not sure what you're asking.
never mind.
No, it's fine. What was the question?
I'll think about it.
Okay.
Thank you.
Oh, so I think what you're asking is, how do we define the strings in the language based on the number of derivations? Leftmost derivations that it has.
I don't know if that's what I'm asking.
Okay. Other questions, though? Okay. So I'm going to move a little bit ahead in the 8 minutes that we have, and then we'll break for today and then have the office hours after that. And we'll finish the topic that we're going to start now on Wednesday. So let's look at our grammar that we just talked about for balanced parentheses, the unambiguous one. The ambiguous one. Well, could we repeat this process where we make SS, then go down to S, SS, go down to S? Could we do that process indefinitely? Could I also do S produce SS and change that first S to SS, change that first S to SS, and repeat that over and over and over, get 10,000 variables, and make them all go to the empty string? Yeah, wouldn't that be kind of annoying? Where we made a whole bunch of variables and they just all went away. Yeah, that might be kind of annoying. And another annoying thing is that we have two ways of making the empty string, at least two ways, and that's also annoying. Wouldn't it be great if we had some procedure that allows us to not only get rid of the multiple ways to get the empty string, but also get rid of this possibility of having variables come into existence and then go away? What we want to do is, when we make a variable present, we want it to make something of the string. We want to have some progress in making this string that we're trying to generate. And something that'll help us do that is something called Chomsky Normal Form. So if you've ever worked with databases or something like that, you've encountered this idea of normal forms. And this idea has been used all throughout computer science. But the idea is, let's try to simplify what the object that we're trying to work with is to have some really nice structure, and then we can analyze it. So we say that a CFG is in Chomsky Normal Form. Or CNF for short. So it gets kind of annoying talking about a CFG and CNF all the time, but that's the TLA, three-letter acronym that we're going to talk about. I think it should be three-letter initialism because that's what it actually is. But all right, So it's in Chomsky Normal Form. If all rules are of the form, well, in order, so what do we want here? We want to be able to convert any context-free grammar into CNF. So we want to recognize still the context-free languages. So what string must I have in order to get the context-free languages? Empty string. And like we just mentioned, we want exactly one way of generating that string. Well, a really easy way to do that is force the start variable to generate it directly. So S goes to empty. And I'm just letting you know right now, this S, this variable S, is going to be the only variable that can make it the empty string. And so therefore, not quite, it'll be the only way of getting the empty string. Well, we also want a single terminal, like we did with regular grammars. So I'm going to allow you to have any variable make a single terminal. So A is any variable. Even the start variable can make a single terminal. Or, well, now like with regular grammars, we needed to go to other variables, but I better not say that you can go to one other variable, because now we're back in the land of regular grammars, and we know some languages are not regular. So why not two? So I'm going to allow you to go to exactly two other variables, with the restriction that B, the things on the right-hand side, are not the start variable. So exactly one way to generate the empty string. Why? Well, there's one way to do it, possibly. S goes to empty string. But could I somehow come back to the start variable and make it another way? No, because the variables on the right-hand side of the rule are never the start variable. So if I apply A goes to B, C, neither of them are the start variable, and so neither of them can make the empty string. So we guarantee there's exactly one way to make the empty string. Oh, that kind of tells us something nice. If I apply A goes to B, C, does B and C have to make something of the string? Yes. Can they make the empty string? No. So every variable you make must make something of the string, which is kind of nice. And something we'll see when we get, actually we have more time, never mind. Something we'll eventually see is that whereas with like grammars that, of any form, we may not know exactly how many applications of rules that we'll need, whereas with here, we'll know exactly how many rules we will apply for any string of any length, which is kind of nice. Okay? Any questions on the definition of CNF? Yeah.
So how do we get back to the S?
Oh, we can't.
We can't.
We can't.
We'll never get back to S.
We'll never get back to S. It's bye. Bye-bye.
We can't process this left as derivation, right?
Well, we may apply A goes to B, C, where B is, then we process B, which is the leftmost variable. That's why I needed two variables there, because if I stuck with one, then we're back in the regular language land. Yeah. Other questions? Yeah.
Does every grammar has a normal form?
Yes, and that's something that we're gonna start today and finish on Wednesday. We'll be able to convert any CFG into CNF, which is kind of nice. And another really cool thing that we'll see, believe it or not, CNF will help us prove that some languages are not context-free, but time permitting. So let's see. Let's copy down the grammar that we had before. And let's work with the one that was ambiguous. So let's copy this guy down. So copy it down. So is this grammar in CNF? No, and it actually breaks quite a bit of rules. It has S goes to empty, which is fine, but it has S going to SS, but S is the start variable, so that's going to cause a problem. And on the first rule, it breaks a lot of rules there. It has mix of variables and terminals, which is kind of annoying. So let's see. How are we going to get it into CNF? Any grammar into CNF? Well, could we get the B, oh, that's not what I want. Could I get B and C not equal to S? Could we fix that rule really easily? Yeah, how can I do that? Create a new start variable. And what are the rules associated with this new start variable? How about I just produce the original start variable? So, step 1 of 5 is make a new start variable S0 with rule S0 goes to S. So if we work with our example, we'll have S0 goes to S. And should I change anything of the original grammar? No, because I want to get the exact same language. So the key thing to think about as we're working through this is we don't want to change the language anytime. And so at the end, we'll guarantee that the language of the resulting grammar in CNF has the same language as the thing before. Thus, we can convert any grammar into CNF. So let's not modify any of the original rules. But let's make sure that, yeah, go ahead. Well, I can't necessarily guarantee that because the original grammar might have some roundabout way of making the empty string. Like S goes to T, goes to A, goes to whatever, and makes the empty string at the end. So I don't know necessarily whether it makes the empty string or not. So that'll be filtered out in a later step. Yeah. So eventually this S goes to empty will propagate up to the S0. Correct. Yeah. So like we could have like some other variable that itself makes the empty string, but the grammar as a whole doesn't make the empty string. Like the only way to get there is produce a character, then that makes the empty string. Yeah, that's totally possible. Other questions? All right, we have a few minutes. So let's think about what should we do next. Well, actually, we should make sure. Did I change the language here? No. Well, let's be absolutely sure. If I had a derivation with the original grammar, do I have one now? Yeah. Well, whatever S did originally to make whatever string, just put on the front of it, S0 goes to S. You didn't generate anything along that rule, so therefore, just do the exact same thing as before. If I have a derivation in this grammar, did I have one originally? Well, this grammar must do as its first step, S0 goes to S. It must. And so therefore, when S makes the whatever string, just take off S0 goes to S at the front. And then now that is a derivation in the original grammar. Questions? Okay, so let's go on to step 2, which I don't have notes for, but I'm gonna try to remember it anyway. Well, let's see. Is our grammar now in Chomsky Normal Form? No, we fixed the start problem. But we didn't fix the empty string problem. Okay? And another thing that we should think, a lot of things we need to think about, but another thing we need to think about is I kind of want these steps as we're doing them to not reintroduce problems that we saw before. So, for example, when we made the new start variable S0, I don't want a later step to cause a problem where S0 appears on the right-hand side. Or like if I have a step of deleting the empty string, I don't want empty string to appear on the right-hand side of some other non-start variable. I want to have steps not reintroduce problems from before. So the problem that we're going to fix now is the non-start variable going to empty string, but we just ran out of time. So let's take a 5-minute break, and I'll have office hours after, but otherwise I'll see you on Wednesday.